All right, I'm going to do this constant velocity review. This is Unit 2. And my name, Mr. McGrath. You really should not be watching this video if you have not already attempted these. So if you accidentally or purposefully clicked to start watching this and you haven't tried these yourself, please pause and try them first. Okay, so for these graphs, these are position time graphs with two objects. Looks like they both start at the origin. The slope of a position time graph is the velocity of something. So this has a steeper slope. That means it's going faster than this one. But they both start at 0, and they're both going in the positive direction. Describe using clear, complete sentences how the motion, not the graph shape, of object 2 differs from object 1. So I think I just said those things. I think I want to say both objects 1 and 2 start at position 0, but object 2 moves faster in the positive direction. That would be fine. You don't have to say exactly those words, but you do need to say, you do need to talk about where they start, what direction they're moving in, like positive or negative direction. These are both positive direction, and which one is faster. Now, why did I say this, not the graph shape? So I think I have had many students in the past who get a little confused here about whether they're describing the motion of an object or the shape of a graph. So what you cannot say, you can't say, for example, object 2 has a steeper slope. That is not true. This object, whatever it is, let's say it's one of those little toy cars. This object doesn't have objects don't have slopes. Well, I guess mountains do, but that's not what we're talking about here. Like what we're talking about here is the motion of this object. The slope of this line is the velocity. An object has a velocity, right? An object has a velocity. An object doesn't have a y-intercept. Like, that's not a thing. So you can talk about the starting position of the objects, and basically you have to lift the information about slopes and intercepts into the context of talking about what the objects are doing. Okay? So don't be telling me about lines and slopes and intercepts. You have to translate that into objects and velocities and starting positions. All right, what did the velocity versus time graphs? This is just like a graph of whatever the slope is. So object 2 has a positive velocity, and object 1 also has a positive velocity, but it's less. Looks like my pen's dying here. Let's switch over to this one. Ooh, it's kind of purple. Like that. What I would be looking for here, they both need to be positive, and one needs to be clearly less than 2. All right, how about motion maps? So they both start at 0, but object 2 is going faster, so the dots will be spaced further apart. You don't need to give me a ton of these dots. I think just enough to get the idea. We go halfway to the next. Okay? How about this? Let's see. So what are these objects doing? Object 1 is the same as what it was doing here, and object 2 is not moving. It has a constant position. Position is same position the whole time. So how do we want to describe that? You could just say object 1 starts at position 0 and moves in the positive direction eventually passing the stationary, which means not moving, object 2. Something like that. Again, you don't have to say exactly those words. Something to get at. Object 2 is not moving. Object 1 starts here. I think you do want to say that object 1 is going to pass object 2, because you could imagine a graph where here's object 2 stationary and object 1 starts here. Like it kind of the same situation as this, but this one never passes. It's like already in front of it when it starts. So I think that passing is important. All right, so object 1, same thing. It's got a positive velocity constant. And here, object 2 is not moving, so its velocity is 0. So object 1 is going to look just like what we did here. And then object 2 is stationary, but it's not stationary at 0. You can't put the dots here because it's already, well, not already, it's sitting there somewhere with a positive position. So you could put it here or here. It doesn't matter to me where you put it. It just can't be at 0. And it's staying there. So if I'm going to do 3 ticks, beep, 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 of the timer, I'm going to do 3 there too. All right? What do we have here? I'm going to make a position time graph. So you need to read carefully here. You need to make sure you understand the difference between a position time graph and a velocity time graph, because I could ask you to do either or both of those, and it's a common mistake that I've seen for students to get themselves into the wrong mode and try to make a position time when they're supposed to be doing a velocity time and vice versa. Position time, when we're talking about constant velocity, those are going to be the graphs that have like straight line, or maybe like for a situation like this where the motion's changing, it's like pieces of straight lines. That's what we are looking at here. So let's see what we got. Bicyclist cycles forward with a velocity of 5 meters per second for 8 seconds. So 5 meters per second, if you go 5 meters every second and you do that for 8 seconds, you're going to go 40 meters. I'll just make a little note of that. There. Stops for 4 seconds, and then turns around and cycles 10 meters per second for 4 seconds. That's also 40. But in the negative direction, turns around. So that's negative 40. Stops for 2 seconds, and finally cycles forward at 7 meters per second for 5 seconds. And that's 7 times 5 is 35 meters. Okay? So I think I'm going to be okay if I'm going to go forward 40, then back, and then forward again. So I'm not going to end up in negative territory at all if I start at the origin. Sorry about this little graph I gave you that it doesn't have that bottom line in it. I'm going to make that my time axis. If I was going to get into negative territory, I might choose to make my axis here so I had some negative stuff to work with. That's why I wanted to go ahead and kind of analyze this before I jumped right into making the graph. All right. So I got my position versus time graph. How about the scaling of it? How much time do I have here? I've got 8 plus 4 is 12, plus 4 is 16, 18, 23. So do I have enough ticks here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Looks good. And let's see, 2, 4, 6, 8, 10. And we'll add some more in there if we need them. And then here, looks like I'm going up to 40, so I think counting by ones is probably not good enough. What if I count by twos? That'd be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 30. That looks like it's going to be pretty good scale there if I go by 2's. Your scaling does not have to be exactly what I choose here, but you should try to use up as much of the graph as you can while still scaling it reasonably. All right, so I already did this, so I think the easiest way to graph this is go out to 8 seconds and say, look, at 8 seconds I know I got to 40, starting at the origin. So that's right here. And then for 4 seconds I'm stopped. So that's going to get me from time 8 to time 12. When you're scaling, when you're writing the numbers on your axes here, you can write or not write whichever ones you want, but every single tick mark has to count as the same value, right? So I can't like decide that this is 8 and this is 10 and then this is 12. Like everything, the spacing all has to be consistent. Turns around and cycles 10 meters per second for 4. So that's back to negative 40. That's going to get me back to 0, and that happens in 4 seconds. So we get to 16 there. We're going back in a hurry. Must have forgot lunch or something. For 2 seconds. And then forward, we're going to get to 35. Over the next 5 seconds. So it's going to look like this. All right. Quick comment about this. What if I had asked you to make a velocity time graph? What would that look like? Well, the velocity time graph, I'll just make a little sketch of it here, because I could ask you to do this on the test. The velocity from here to here is 5 for the first 8 seconds. And then for the next 4 seconds, it's 0. And then for the next 4 seconds, it's negative 10. So if that's 5, then like that'd be negative 5, negative 10 be down here. And then for the next 2 seconds, it's 0 again, and then it's 7. So it would look like that. So velocity time graph is like these pieces of horizontal lines, right? Or maybe in the simplest kind of situation, like number 1 and 2, just horizontal lines, because there's no change in the motion here. So make sure you understand whether you're looking at trying to make a position time or a velocity time. All right, what's the displacement for the entire trip? Displacement is delta x is the symbol we use for that, or you can just call it displacement. It's the change in position, which means final position minus initial position. I ended up at 35, and I started at 0. Oops, I had to write an m there. 35 meters. And then if you know what displacement is, average velocity is equal to displacement divided by time. So the displacement is 35 meters, and the total time is 23 seconds. So whatever that is, 35 divided by 23, 1.52 meters per second. What's the total distance traveled for the entire trip? So total distance, nothing cancels out. I'm interested in all of the distance traveled, whether it's positive or negative. We're taking the positive distances. So kind of did that here, right? 40 and then another 40. I don't care that it's negative. So 40, 40, and 35 are the legs of the trip. 40 plus 40 plus 35 is 115 meters. And then average speed is, if you know total distance, which we do, then you just divide that by time. So 115 divided by 23 is 5. All right. I promise you I will ask you some questions like that. I think this review is like a pretty reasonable idea of what the test would look like. Shown below is a velocity, velocity time graph. Okay. So that's the pieces of horizontal lines. So what's going on here? I've got something that for 2 seconds, for the first 2 seconds, it's going positive 4. For 2 seconds, object moves in the positive direction at 4 meters per second. And then it turns around and goes, for 1 second it goes 3 meters per second in the negative direction. Don't say that it goes negative 3 meters per second in the negative direction, or that it turns around and goes negative 3 meters per second. You want to leave that as the speed and then describe the direction. In negative direction, and then it stays still for 2 seconds. You don't have to say which direction it stops in, because it's stopped. That doesn't have a direction. All right, to draw a corresponding position versus time graph, so this is going to be straight lines, and these are the slopes. Now, where does the object start? It doesn't actually say. It just gives us the velocities. So you could actually start it anywhere, but if you can start it anywhere, aren't you going to choose to start it at the origin? That's probably the easiest thing to do, but it wouldn't be wrong to start it somewhere else. I have a total of 5 seconds here, so 1, 2, 3, 4, 5. And it's going to go forward. Did you remember that if you go 4 meters per second for 2 seconds, it's going to go 8 meters. 1, 2, 3, 4, 5, 6, 7, 8. Did you remember that the area, that area thing, this is a 4 by 2 rectangle. That's 8 meters. This is 1 by negative 3. That's negative 3 meters, and then that's 0. So those areas give you the displacements too. So in 2 seconds it gets up to 8, and then 1 more second goes by and it goes back 3, and then for 2 seconds it stays still. Right? Good. How far did the object travel in the time interval from 1 to 2? On time 1 to time 2, well, it's going 4 meters every second, so you could look at it as the area of this. You can look at your position time graph, or you can just think about what's going on. The answer, no matter how you slice it, is 4 meters. It went from 4 to 8. Find the displacement from time 0 to time 5. And explain how you got your answer. So at time 0, it's at 0, and at time 5, it's at position 5. So I think if you write out that formula, this is an explanation of how we got the answer. Final position is 5, initial position is 0. All right. Consider the position versus time graph for Flipper below. Flipper's a dolphin, in case you didn't know that. Determine Flipper's average speed. Show your work. So average speed is equal to the total distance over time. Total distance, starting at 10, going to 40. So not turning around, so it's just 30 meters. And time, going from time 0 to time 6. That's it. Write a mathematical model. That means mathematical model means an equation for the relationship between Flipper's position and time. So that's an equation of this type. Position is equal to constant velocity times time plus initial position. Right? That's our position equation. So x equal, it's basically like writing the equation for this line. But you cannot do it in like y equals x form. It has to be with the right letters. So x equals, this is the slope here, which I found, times time, plus the initial position is 10 meters. So common mistakes to make here is to write it as y equals x, to go back to math class mode. And also, common mistake is to forget to put units on these things. That has to have units, meters over seconds, because it's rise over run, it's the slope. And then this is the intercept, which has units of whatever the y-axis is, which is position. All right, so please don't forget those units. And last page. For problems 6 and 7, we have a position time graph. We want to make a velocity versus time graph and a motion map. Okay? So here, for the first 1 second, the slope of this is 2 over 1. So the velocity is 2, because that's the slope of this. And it happens just for that first 1 second. And then here, it looks like the slope is 1/2. So that's the velocity for the next 4 seconds. Right? You can do that. It's not hard. Here, same first second. We have a slope of 2, and then a slope of 0. And then a slope of, looks like I have a rise over run -4 over 3. So -4 thirds. That's -1 1/3. So something like that. I think I'd probably be pretty lenient about exactly where in between -1 and -2 you put it. But it's got to be in between those two. So that's what that looks like. Oh, I skipped the motion map for this one. Sorry. So let's see. It starts at 0, at time 0, and then at time 1, it's at 2, at the next tick, and then at time 2, it's at 2.5, and then 3, right? Like that. Ends up at position 4. And then I make my lines that go halfway to the next dot. And the length of those little lines is directly proportional to where these are, right? That's 2. That's like 2, and these are like little 1/2s. Okay? And number 7, our motion map. This time I'm starting at 2. I'm going to put these ones underneath. I'm going to have a turnaround, so I'm anticipating that. You don't have to put them out, put them on top. So at time 0, I'm at position 2. At time 1, I'm at position 4. At time 2, I'm still at position 4. And then at time 3, I'm at, looks like that's 2 2/3 is about here. And then at time 4, I'm like 1 1/3 is about here. And then at time 5, I'm back to 0. That looks pretty good. That wouldn't have to be perfect, but you want them to look as evenly spaced as possible. So I started here, draw a line, goes halfway to the next dot, and then these are stationary, so I never draw up and down lines. So there's no line coming from this one, because it's not moving. And then here, halfway, halfway, halfway. And that's it.